Welcome to This Explainer. Today, we're diving into the truly fascinating life cycle of a memory. We often treat our memories like perfect little video recordings of the past, but the biological reality, it's far more complex, super dynamic, and incredibly selective. From a memory's microscopic birth down at the cellular level, all the way to its systematic decay and active deletion, we're going to explore exactly how your brain selects, stabilizes, and yes, systematically forgets information.
So, to keep us moving, here's our roadmap for today. 1. The brain's memory matrix. 2. The 4 stages of memory. 3. Synaptic plasticity. 4. Why we actively forget. And 5. Optimizing your cognitive lifespan.
All right, Section 1, the brain's memory matrix. Let's dive right in and actually map out where these memories live in the physical architecture of your mind.
Before we start poking around brain regions, we really need to distinguish between our two main memory systems. First up, we have explicit memory. These are the conscious facts and events you can declare outright, like what you had for breakfast or knowing the capital of France. On the flip side, we have implicit memory, which operates entirely under the radar, unconsciously executing motor skills, habits, and reflexes. Now, this functional split was famously proven by patient HM. He was a man who had a surgery that removed his hippocampus, and boom, he completely lost the ability to form new explicit memories. But here's the crazy part. His implicit memory was perfectly fine. He could learn and master complex motor skills, like mirror drawing, without any conscious memory of ever practicing them. You actually might recognize this exact biological quirk from the movie 50 First Dates, where the main character basically suffers an encoding failure for new facts, but keeps all her procedural skills intact.
What's really cool is how our physical biology perfectly maps to these systems. For your explicit memories, the hippocampus is essentially your brain's indexer, organizing all those sensory inputs. Right next door is the amygdala, handling emotional balancing, basically tagging memories with emotional weight so we remember what's a threat and what's a reward. Then the prefrontal cortex jumps in to manage our working memory and executive control. But check out our implicit, unconscious skills. They rely on completely different hardware. The cerebellum handles your fine motor learning and reflexes, while the basal ganglia automates those complex habit loops. So memory isn't just one thing sitting in one place. It's a highly distributed matrix.
Moving to Section 2, the 4 stages of memory. Let's transition from the anatomy to the actual operational timeline of how a memory is processed.
Every single explicit memory has to survive a pretty strict 4-stage gauntlet. It kicks off with encoding, where sensory stimuli get converted into electrical signals. But this absolutely requires selective attention. If you're distracted, the memory simply never enters the system. Gone. Next is consolidation. Think of short-term memory like a pile of loose Lego blocks on the floor. Consolidation is the active biological process of snapping those loose blocks together into a cohesive structure. The hippocampus actually replays these neural patterns, especially when you're in deep, slow-wave sleep, to lock them in. Then we hit storage. But remember, there's no centralized hard drive in your brain. Visuals go to the occipital lobe, sounds to the temporal lobe. They're scattered across the exact same networks that originally processed the event. And finally, retrieval, the conscious reactivation of all those highly distributed networks.
So, the huge takeaway here is that retrieval is definitely not just pressing play on a static video file. It's a real-time, highly active reconstruction of those scattered Lego blocks. Because of this, your ability to pull a memory back up is heavily governed by the encoding specificity principle. Basically, this means you'll totally maximize your recall when your current physical, emotional, and environmental conditions match the precise conditions of when you first learned it. Your context literally acts as the key to unlock those distributed networks.
Section 3, synaptic plasticity and memory. Let's zoom way in to the microscopic level and see how those Lego blocks are physically glued together.
The true biological engine of memory is a process called long-term potentiation, or LTP. When you learn something new, your neurons literally have to strengthen their chemical connections. Here's the mechanics of it. You've got 2 main receptors, AMPA and NMDA. Normally, the NMDA receptor is physically blocked by a positively charged magnesium ion, kind of like a locked door. But when neurons fire in really rapid, high-frequency bursts, a massive amount of the neurotransmitter glutamate is released. This depolarizes the membrane and literally, electrostatically repels that magnesium block right out of the way. Once that door is open, calcium ions flood into the cell. This calcium surge is a powerful messenger.
It activates specific proteins that build new AMPA receptors and actually expand the physical size of the synapse, making the connection permanently stronger. That structural change, that is literally what a memory is at the cellular level. And this brilliantly illustrates the biological push-pull dynamic going on in your head. When calcium floods in, it activates a kinase called CAM-KI, which drives all that synaptic strengthening we just talked about. But to keep things balanced and prevent runaway strengthening, because we need our brains to stay flexible, we have an opposing force, a phosphatase called PP1. PP1 actually weakens synapses in a process called long-term depression. It's a lot like a rubber band. You need that dynamic tension. If you constantly stretch a rubber band without ever letting it relax, it either loses its elasticity or it just snaps. This delicate balance between CAM-KI building things up and PP1 pruning them down ensures we only store what's biologically relevant without completely frying our neural networks.
Section 4. Why we actively forget. Time to completely flip the script. Forgetting isn't a glitch, it's a feature. It's an adaptive biological necessity to keep our minds from severe informational clutter.
Which brings us to a rather harsh reality, first mapped out by a scientist named Hermann Ebbinghaus using his famous forgetting curve. 50%. Over 50% of newly acquired information is completely lost within the very first hour if you don't actively reinforce it. The decay drops off incredibly fast right after learning and then kind of stabilizes. But think about it, if we didn't have this active clearing mechanism, our brains would be totally overwhelmed by useless everyday static.
Now, besides simple trace decay over time, we also deal with interference. And this is a two-way street. Proactive interference is when old, deeply consolidated memories actively block you from learning something new. The classic example, changing a password. Your brain is so intensely wired to the old one that it actively trips you up when you try to use the new one. On the flip side, we have retroactive interference. This is when acquiring new information overwrites or disrupts the old stuff. So if you move and memorize a new home address, you might suddenly find it surprisingly hard to recall your previous one. Those similar memory traces are basically competing for access.
But often the memory hasn't decayed and it hasn't been overwritten at all. It is safely stored, but we hit a temporary retrieval roadblock. This is perfectly captured by the highly relatable and incredibly frustrating tip-of-the-tongue state. You know the memory is in there, you might even know what letter the word starts with or how many syllables it has. But a localized block stops you from grabbing the complete target. It's absolute proof that there's a massive difference between a memory being physically available in your brain and actually being accessible to you in that exact moment.
Finally, Section 5, optimizing your cognitive lifespan. Let's take all this neurobiology and turn it into some actionable strategies to preserve our minds.
To actively combat that steep Ebbinghaus forgetting curve, cognitive psychology tells us we need structured retrieval methods. First up is the spacing effect. Basically, spreading your learning out over time instead of cramming. This gives your brain multiple sleep cycles to replay and stabilize the network. Second is the testing effect, forcing your brain to actively retrieve the info rather than passively rereading a textbook. That active recall directly triggers the long-term potentiation we covered earlier. And third, overlearning. Practicing well past the point of just getting it. This builds a highly resilient network of association cues that are practically bulletproof against interference.
And hey, going back to our rubber band metaphor for a second, those synapses need the right metabolic fuel to stay flexible. Two big dietary modulators really stand out here. First is choline, which you can get from eggs and soybeans. It's a direct precursor for acetylcholine, a neurotransmitter that is absolutely critical for attention and encoding in the hippocampus. Then we have omega-3 fatty acids, specifically DHA, which you get from fatty fish. DHA literally makes up 30 to 40% of the polyunsaturated fatty acids in your synaptic membranes. It maintains the physical fluidity of the cell walls, which, amazingly, is a hard biological requirement just to initiate LTP.
Lastly, if we want to optimize, we have to play defense against Daniel Schachter's 7 sins of memory. He splits these systemic failures into 2 groups. First, errors of omission, where the info is just lost. This includes absent-mindedness from not paying attention, transience over time, and blocking, like that annoying tip-of-the-tongue state. But the second group is even wilder, errors of commission, where memories are actively distorted. Things like misattribution, where you remember a fact but totally forget where you heard it. Suggestibility, where a leading question literally overwrites your memory of an event. Bias, where your current mood rewrites your past. And persistence, which is the unwanted intrusive recall of traumatic events.
All of this leaves us with a pretty profound question to chew on. We've seen today that every single time you recall a memory, you are not just hitting play on a tape, you are physically rebuilding it in real time, combining scattered fragments with your current emotional state, external suggestions, and hidden biases. Given that reality, how much of your own personal history,
The very stories you tell yourself about who you are is actually an objective record, and how much is just a highly structured, continually updated biological illusion. Thank you so much for joining me on this explainer. Keep learning, keep questioning, and definitely go reinforce those synapses. Catch you next time.